I think they're good.
It usually asks me if I'm okay with recording, but
It didn't.
right. But okay, let's hope it works. All right, let's start. So welcome everyone to this webinar. Today we're going to be talking about adding and managing GPUs on Kubernetes clusters. And it will be presented by me, Dana Gaponchik. I work in the IT CD PI section. So let's start with some basic introduction. So in order to create a Kubernetes cluster with GPUs assigned, you just need to provide this extra label on cluster creation, which is NVIDIA GPU enabled true. This is enough to get a cluster back, but by default, you have only two nodes that are deployed. One is the master node and one is the worker node, but you get no GPU yet. So even though your cluster is capable of managing GPUs, you don't actually get a GPU by default. In order to get a GPU, you need to go to this table. This table can change, so make sure you visit the link and you get the latest flavor. And you need to see what GPU flavors are available, but also you might need to open a ticket with the responsible functional element to make sure that you have quota for a certain GPU, because GPUs are expensive and scarce, so the assignment of GPUs is something that people are monitoring closely. So make sure you have the right access before trying to create a cluster with GPUs. Since you know you already have access, you can take the flavor from here and then create a node group with the flavor that you chose. In my case, I'm using G2 5x large. And if we go back to the table, this is the equivalent for a T4. And after quite some time, a few minutes, you get the node group creation completed, and you get your node, which in my case, as I said, it's a T4. When you get this new node, on the node, you'll get a few pods running from the NVIDIA GPU operator that will make sure that you can manage the GPUs on the node. So you get these components running on your node, making sure that the GPUs are functioning and you can allocate them and use them properly. So first of all, you have an NVIDIA driver daemon set, which is a component that is aware of your kernel version, your OS version, and actually loads the drivers on the node. So you don't have to care about this yourself. Then we have NVIDIA Container Toolkit, which makes the container runtime aware of how to run containers that have GPUs or need to use the GPUs. Then we have NVIDIA DCGM Exporter, which stands for Data Center GPU Manager, which is a suite of tools for managing and monitoring NVIDIA data center GPUs. This is also a component that makes sure your GPU metrics are available to Prometheus, so that then we can do nice visualizations with them. And NVIDIA Operator Validator, which does what the name suggests. It validates that the installation until this point worked properly. Then we have NVIDIA Device Plugin Daemon Set. This is a component that is aware of Kubernetes in Kubernetes context. And this is the component that makes the NVIDIA.com GPU resource type available on the cluster. And then we have NVIDIA CUDA Validator, which validates that the stack installation worked properly and you have CUDA. Next, we have Node Feature Discovery, or NFD. This is a dependency of a GPU operator. And this populates the node with certain so-called features. In this case, we have a lot of features related to NVIDIA, like the CUDA driver version, like what type of GPU you have, what is the architectures, how many are there, and things like this. And by only having this, basically you don't need to configure anything additionally. You already have a GPU available, allocatable on your node. You can use this resource, which is NVIDIA.com GPU, to actually create a pod that accesses the GPU. And you can see that with this simple YAML, we can already create a pod and exec into it. And we can do NVIDIA SME and see what we have available. So tainting the nodes, this is very important in the Kubernetes context because we don't want workloads but don't require a GPU to end up on a node with GPUs. So as a result, it's very important to make sure that your GPU nodes are tainted. We currently do not taint by default the nodes that have GPUs. So you have to do this manually, but a small disclaimer is that we are working on a solution for this. So in the next release, we will come up with a way to have automatic tainting for the GPU nodes. All right, so now we can actually look into some example use cases. And I chose some use cases that have different GPU consumption behavior. First of all, we have a badly coded simulation job. This would be a workload that has low GPU utilization. It's a long-running process, but doesn't utilize a lot of the resources, so a lot of them are actually idle. Second, we have an inference service, which is occasionally triggered by outside events. In this case, this is a workload that utilizes a lot of GPU power, a lot of GPU cores, but it mostly sits idle because it's an example of a spiky workload. So only when the external entity is triggering the inference service, we're actually gonna get a load. Other than this, we're mostly just sitting idle. And lastly, we have a notebook user, and in this case, we don't know what to expect. We can have potential memory leaks or poorly considered batch sizes, but at the same time, maybe our user will allocate a GPU and not even use it. We have absolutely no idea to know this in advance. And just also a disclaimer, all the use cases were run on a CERN Kubernetes cluster with one NVIDIA 140GB PCIe GPU. All right, so now we onboard use case number 1 on our full GPU, and we monitor the GPU utilization and memory utilization. And what we can immediately notice is that the GPU is underutilized. The memory utilization is stated, but also is very, very low. It's only 20%. And one conclusion we can have here is that it's nice to have access to a full GPU, but some use cases cannot fully utilize the full GPU, and this results in a lot of idle time. Also, if you have dedicated GPUs, you have a smaller and a limited GPU offering because we can only have so many GPUs here locally at CERN. So how can we improve this? To improve this, we have to start thinking about GPU sharing. And the easiest way to share is time slicing. Time slicing means that our scheduler will give an equal share of time to all the processes that were scheduled on the GPU. So this process gets a time slice, that's why it's called time slicing, and the memory is available to all the processes to get. To enable time slicing on your cluster is fairly easy. So all that you see in the middle is YAML that already exists on any Kubernetes cluster that was created with a label we mentioned at the beginning. So as a result, the only thing that you have to do is to label the node with a certain configuration that you want. In this case, we have slice 4. This is what we have also defined in the config map NVIDIA time slicing config. And then by just labeling the node, you can see that in allocatable on the node, we get GPU.shared 4. And now we can use this GPU.shared as a resource type in our limits to create a pod that will be scheduled on a time sliced GPU. So now again, we have use case number 1 running on the GPU. It's what we saw in the beginning. But now we can actually schedule use case number 2 as well with time slicing GPU sharing. And you can clearly see the spikes in memory when use case number 2 is running, because we said that use case number 2 is quite spiky. And overall, the GPU utilization improved. It's much better, but still we can get more out of this single GPU. So as a result, we tried to onboard use case number 3 as well. And we just wait for a bit and see what happens. So this is use case 2, and now we have 3 as well. And we can start seeing that the GPU utilization is 100%, which is what we wanted. Like the memory utilization is very good, the GPU utilization is very good. So this must be perfect, right? Well, not really, because in this particular use case number 3 tried to allocate all the memory available on the node and start use case number 1 and 2. And to actually graphically show this is what happens. So a full GPU is like a ship, a big ship, and this ship has enough space for use case 1, 2, and 3. But 3 wanted to be greedy, so it just pushed use case 1 and 2 out of a ship. So now they are drowning, while use case number 3 is just relaxing with all the resources that he has. So to sum up with time slicing, the good part is that it works on a very wide range of NVIDIA architectures. It's very easy to set up, and in theory, we have an unlimited number of partitions. But the disadvantages is that you don't really get process or memory isolation. You cannot set priorities between your processes. So as a result, it's just inappropriate for anything that is very latency sensitive. So to do better than this, we need to look into a more elaborate way of GPU sharing, which would be multi-instance GPU, or short MIG. MIG means that we can partition a GPU into up to 7 instances, where each instance is fully isolated with its own high bandwidth memory, cache, compute cores. So one full GPU, as soon as we enable MIG on it, in case of A100, a full GPU is the equivalent of 7G 40GB in MIG. So this is your full GPU, and you read it as 7 compute cores and 40GB of memory. And then you can partition this full GPU into smaller instances as per this table. You cannot just randomly assign a random amount of cores or memory. You should follow this table. So you can do 3G 20GB, you could do 2G 10GB, or 1G 5GB. And you can also do combinations of both. Very important is to make sure that the total sum is what you started with. So for example, if we do the full GPU, if we partitioned it into 7 instances of 1G 5GB, in total we would have 7G 45GB, which means by just partitioning it like this, we lose 5GB of memory, which is not good. So this is something to always keep in mind when choosing a certain partition. Also very important with MIG is the so-called MIG strategies. By default, we deploy in our clusters the MIG strategy, which means that every MIG device is advertised as the resource type with the name of the instance it represents. So if we have 3G 20GB, then the resource type in Kubernetes that is advertised, it's called NVIDIA.com MIG 3G 20GB. If we go for single strategy, all the devices will be called NVIDIA.com GPU. So you will not know what kind of MIG device you have behind. And none means that if there is no distinction between the GPUs with MIG or without. To enable MIG again, it's fairly easy if your GPU supports it. So you can see the mix strategy is mixed. This is by default on our clusters. Again, all the YAML that is in the middle is just deployed by default on our clusters. And then we have a config map as well available, which is called NVIDIA MIG config, where we define many types of MIG configs. So you can take a look as well here to see which one is makes more sense for your use cases. And to actually enable MIG on one of your nodes, you have to label your node with this particular label, which is NVIDIA.com MIG config, and then the name of the config that you want. And you can see that after a few seconds, up to a minute, you will see in the allocatable table now your particular MIG instances that you chose. And you can use the name of a resource to create a pod that will utilize this instance. So now if we run use case 1, 2, and 3 again on one GPU with MIG, we can immediately see that we can have monitoring per process, which is really good, because before we had to guess, does it work? Which process is consuming how much? Things like this. Now we are quite sure, and we can have per process monitoring, which helps a lot. So now every process is isolated, saturates its own resources, and cannot influence other processes. So this is perfect, right? Well, actually, yes, because use case number 3 tried to allocate more memory than available to its own instance, and it couldn't because it's isolated, so it started itself, while use case 1 and 2 continued running. So if we go back to the animation, this is kind of what happened. So we don't have anymore the big ship, which was the full GPU. We have smaller boats for every MIG instance, and every use case has its own small boat. And when use case number 3 tried to allocate more than available, it, instead of throwing 1 and 2 out of a ship, it threw itself out of a boat. So to go back to advantages and disadvantages, MIG is really good because you have hardware isolation. You can come up with certain guarantees in terms of performance, and you have monitoring and telemetry data available at the partition level. And it's very flexible in order to choose which layout is best for your use case. But the disadvantage is that this is available only for Ampere, Hopper, and Blackwell architecture. Reconfiguring will require to evict all the running processes. And as I mentioned before, there might be some potential loss of available memory or even compute, depending on the chosen layout. So you have to be very careful and informed when you choose a layout. All right, so now we can talk about the trade-offs, because for sure sharing cannot come for free. And in order to put some numbers on this, we need to perform some benchmarking. In our case, what we did is we came up with a simulation script that generates collision events that was built with Xsuite, that is very heavy on GPU usage, but is low on memory accesses and low on CPU to GPU communication. And again, we're running on an A100 using a Kubernetes cluster. So if we take a look at the time slicing performance, if we run only one process, and let's take the biggest input, which is 40 million, one process, one simulation can run in 152 seconds. We would expect in an ideal world that if we schedule two processes, it would run in double the time, which is 305 seconds. In reality, this number is closer to 423 seconds. So we have a performance loss of 48%. And this is due to the context switching that needs to happen on the processes that are scheduled on the GPU. This is a lot, so this is something to keep in mind. But at the same time, if we schedule more processes than two, like 4 or 8, we don't have additional performance loss. With MIG, the math is a bit differently. So with MIG, a full GPU has 108 streaming multiprocessors. And this is what directly influences the amount of CUDA cores and tensor cores we have available. When we enable MIG, we immediately lose 10 streaming multiprocessors, or SMs. And you can see that this directly influences again how many CUDA cores and tensor cores we have available for our workloads. So we lose 9.25% performance just by enabling MIG. And you can see that if we actually try to run the benchmarking or simulation on a full GPU without MIG and one with MIG, we can see the theoretical loss in practice as well. But then when we take smaller partitions and we take a look at the scaling between them, the results converge to ideal values. So to conclude, I would say that MIG is suitable for most use cases because it behaves and feels like a separated dedicated GPU, but this is not true for time slicing. Time slicing is good for something that is a bit low priority. It can be good for interactive workloads, but because independent workloads can trigger errors, you have to come up with an external mechanism to actually control the memory usage. And if necessary, you have to evict a process that is trying to consume more than available or allowed. But time slicing is not good for something that is very latency sensitive or something that is very performance intensive. In terms of monitoring, if you just create a cluster with NVIDIA enabled through like we talked in the beginning, and monitoring enabled, you get this nice dashboard with a lot of information that is very useful when you're trying to debug or monitor your GPUs. And this dashboard we created for us, but also we published it on Grafana Labs. So it's public if anyone wants to take a look. By default, there are many things that are available to monitor. but sometimes we want to monitor something more specific that is not just available by default. So if this is the case, you can go to this link and take a look at the available field identifiers, and then enable the field identifiers that are relevant for you and your use case. And then you will be able to do nice visualizations with specific metrics that are not available by default. GPU access with Kubeflow. So there is also an option if you want to use GPUs to not create a cluster and deploy everything yourself, but use a managed service like Kubeflow, where you can create notebooks without problems. To find more, you can take a look at ml.cern.ch or mldocs.cern.ch. And to conclude, it is quite easy to create a cluster with GPU nodes because the user is abstracted away from anything that is related to setting up the drivers, versions, and other issues. So it should just work. And when it doesn't, you can just open a ticket with us and we'll take a look why. So GPU sharing is very useful to improve our overall GPU utilization, but it comes with certain performance trade-offs. So sharing helps us to offer GPUs to more users, but at the same time, for the use cases that can fully utilize a GPU, we need to consider allocating dedicating GPU. Third, monitoring is extremely important, but the current infrastructure we have is flexible enough to cater for very, very different use cases. So I think we're good in this regard. And four, if you have ML workloads, maybe consider using Kubeflow. Thank you. So this is what I had prepared in terms of slides. So now we can take a look at a small demo. Just confirm that you can see everything. I will try to make it a bit bigger because I'm assuming cannot properly see everything.
We can see your terminal. Yes, this
can
side
see.
is good.
Perfect. All right, so what I will do, I'll check if I'm connected to the right cluster. Okay, I am. So I created a demo cluster that has a GPU assigned to it. So my node group is called GPU. So first what we're gonna do is we're gonna describe the node that has a GPU assigned, and we're gonna see what GPU we have. So if we go to the allocatable table here, this is the result of things that we can allocate on a node. We can see that indeed we do have a GPU available that we can use. And if we go to the labels, we can see that we have an NVIDIA A100 PCIe for the GPU. And also the strategy is mixed. As I said, this is the default thing. So now what also we can do is we can do a get pod in the kube system namespace. We can grab for NVIDIA stuff, and we will see that we have NVIDIA Container Toolkit, CUDA Validator, DCGM Exporter, and other components that I mentioned in the presentation. Next, we're gonna try to exec into one of the pods, in this one, in the DCGM Exporter. So if we try to go here, and we run an NVIDIA SME, we can see that we indeed have in A100, we can see what is the memory utilization, what is the GPU utilization, and what is the power usage, and what is the driver version, everything that is relevant for your GPU. Next, what we can also do is we'll try to exec into the same pod from here. Am I connected to the right cluster here? Yeah, all right. In Cube system, so it's NVIDIA, DCGM. All right, so on this part, I will try to monitor. I will actually try to make it a bit smaller to make it okay. So, all right, we can see here what is the memory utilization, and in this we can see what is the current GPU utilization. And here I'll try to run a command, which is DCGM. Okay, DCGM prof tester, don't have prof tester. It's not available, why not? Okay, live demos as usual. Very weird that it's not available, DCGM. Okay, now it is, I don't know why, okay. So DCGM prof tester, then I think it's no DCGM validator. then it's gonna be 107 minus d, let's do 60. So what I will do, I will try to create some test load. And this means that the load created will be in floating point 32, and the duration will be 60 seconds. And of course, I did something wrong. No DCGM validation, not validator, okay. Validation, all right. Okay, so now it's running. You can actually see how many flops we can get out of our full GPU for, in this case, floating point 32. And you can see that the GPU is 98% utilized, 97. You can see also the memory consumption here, which is quite cool.
Diana, can you please reduce the size of your terminal on the right?
Can you come again? What?
Can you please reduce the size on the right terminal?
I tried, but I don't know how to do it, to be honest. I can just create another one. All right, I'll go to export the right thing again. All right, should be it. NVIDIA SME. And we're gonna watch it. I think now it should be better. Okay, this should be better. All right. Yeah, so you can see it's quite nice. It's gonna run for only 1 minute, but you can do this with different data formats and for different durations and different GPUs. It's a very powerful tool that we use for benchmarking as well. So now since I created a bit of load, what I want to do is I want to try to port forward the Grafana and go then here to, I believe I put 5,000. All right, so I have my Grafana available here. And if I go to dashboards, video GPU, so if we put only 40 minutes, we can see that we have some activity here from what I just ran. We can see that we have 1 GPU only. You can see the GPU utilization. If we put a bit more, like 1 hour, you can see that I tried to run other stuff as well before lunch, I believe. Yeah, you can see it here, I think. All right, so this is what, okay, by the way, the memory utilization is not available. I don't know why, because for some reason we closed. Okay, but the memory is working as well. So just by creating a cluster with monitoring enabled and NVIDIA enabled, we can get nice visualizations already, which is nice. I will close this here. So now what I want to do is I want to make this a bit bigger. So what I want to do now is I want to try to enable time slicing. So to do so, I'll have to, so it's going to be kubectl label. Yes, okay. So I need to provide here the node name. So it's going to be the node that has a GPU assigned, and we're going to use, I had this in the slides as well. So this is the label that you need to use up until config to enable time slicing. And then this is the slice that I want to use, the configuration that I want to use, which means time shared between 4 processes. And then after I label this, I can describe my node again. And if I go here, I can see that GPU is 0 now, but GPU shared is 4, which means I can assign this GPU to four processes at one time. I can also do a get config map in kubesystem and grab for time slicing. Yeah, it's this one, right? So it's NVIDIA time slicing. And if I do a YAML, I can see that I have two configurations available in the cluster by default, which is slice 4 and slice 10. Slice 4 means it's going to be time shared between 4 processes. Slice 10 means it's going to be time shared between 10 processes. One thing that you should also be aware of is that if you enable time slicing, none of the NVIDIA component restart. So they started 1 hour ago and they're all here, nothing happened. Now what I'm gonna do is I'm gonna disable time slicing. So I'm gonna remove a label, all right. I'm gonna describe the node again, just to be sure so it still didn't do anything. Allocatable, I think like this, to be more specific, and we're gonna take, yes, all right, so now it worked. We have only 1 GPU again, and we have none that are shared. So now I can try to enable MIG. So for MIG configurations that are available by default in the cluster, there is also a config map, NVIDIA MIG config. We take the YAML of this as well. We have many more than we had for time slicing. So you can choose whatever that you want from this list. You can have 1 3G, 20 GB, and 4 for 1G, 5 GB. Depending on your use case, you can choose what you want. So I had somewhere an example when I was preparing this. We can choose, I'll try to find, yeah, I was using this one. So we will use this one as well. Okay, so label the node, and then we provide the exact configuration we want from this list, and this is the label that you need to use. All right, we labeled. So in case of MIG, you should see, yeah, so I was kicked out of this pod, because with MIG, the pods in Kube system related to NVIDIA should actually restart. So yeah, we can see terminating init. Not all of them, but some of them will have to restart to make sure that the new configuration works. So now we can watch this until they are running fine. Hopefully they are. I think sometimes the GPU operator can get a bit confused if you change the configuration too fast, or maybe it doesn't like something. In debugging, it's quite hard. So I hope it's just gonna work, but we'll see. Okay, I need 1 out of 4. Something new, completed, initializing, please. All right, running. Okay, we have an error here. Not good. Gonna wait for a few extra seconds, maybe it comes back. If we take a look now at our node, what do we have? Okay, so MIG worked. So I hope, yeah, okay. So it came back all good. It was just a timing issue. So now if we take a look at the node, we have 2 MIG devices, 2G 10 GB, and 1 MIG device, 3G 20 GB. And what I said about making sure we don't lose resources, if you sum this up, you'll see 7G 40 GB, which is actually the full GPU. So we're not losing anything. All right, so now if I try to create, what should we do now? I think the nicest thing that we can do actually is kubectl. Right, let me think. No, so one thing that I wanted to do is I wanted to try another configuration as well, which would be, if I have a config map available here, it's this one. All right, 7G. So let's see. Yeah, I need to overwrite. Right, labeled. Let's see if the pods again, they restart nicely or not. Init terminating, okay, as expected. So with a new configuration, I should get 7 instances of 1G, 5 GB. In this case, all the instances are the same, but the problem is we lose 5 GB of memory, which is not good, but it's fine in terms of the demo today. In reality, you'd have to think twice before doing that. But maybe in case of your use case, it makes sense to have slices that are the same, and you want to keep them consistent. Right, so we have to wait again, pod initializing. We wait for a bit. Okay, if we do a describe again on the node. Okay, so now everything else is 0, and we have 7 instances of MIG 1G 5 GB. All right, all good. All of them are happy. All right, so what I want to do next is I want to edit. I'm gonna show first. So if you get the CRDs that you have in your cluster and you grab for NVIDIA, you'll see these cluster policies. So what we can do is we can edit the cluster policy, which is called cluster policy. We can search for strategy here. Strategy, all right. And we have mixed, we can use single. We're gonna try this out. Again, we have something that is terminating, which is fine. So if we do a describe now, okay, all of them are 0. So in principle, we should get NVIDIA.com GPU available in a few seconds if this works as expected. Okay, we see something in terminating and something in init. We need to give it a second because these things require pod restarts. And they require a bit of synchronization between the processes. So we'll have to wait for a bit. Okay, this one as well. Completed. Okay, and the validator. All right. So if we describe again, all right, here it is. So we still have MIG devices. We don't have full GPUs, but because the strategy is not mixed anymore, but it's single, all the devices are still available under NVIDIA.com GPU. You can see that we have 7 because this is how many slices we have. So one thing we can do now, we can also, pipctl label. What we can also do is we can try to enable time slicing and MIG at the same time. And I'm going to use slice 10. And if we describe now, we should get 70 available NVIDIA.com GPU shared. Yes, exactly. So now we have 7 MIG slices, and every slice is partitioned into 7. So now we have 70 available GPU shared instances. I'm not sure you want to do this in the real life, but it's quite fun to do it for a demo. I have a pod prepared here, but it's just running Python and is requesting a GPU shared. I want to show you that this is just a Python image. This is not something NVIDIA custom with drivers or anything. This is just a simple Python image. So I don't mount anything. I don't have to make it higher priority or anything, or have special security things, nothing. By just having a Python image with nothing related to NVIDIA, I can still run this. So if I run this, and we get the pod, and we wait for a bit because it needs to be pulled on a node. Hopefully it doesn't take too long, because in this case, it's just Python. It's not a big image or anything. All right, it's running. So now we can try to exec into it. So it's Python. All right, so now we're here. If we do NVIDIA SME now, so what we can see, first of all, we have NVIDIA SME, even though this is just a Python image, so everything works. Your pod is configured to have access to GPUs and to all the necessary binaries just because the GPU operator knows how to do it, and you don't have to care about this or configure additional things. Next, what you can see is, again, NVIDIA SMI version, driver version, the fact that you have an A100. But since you are running on a MIG device, you can see MIG devices now. And you can see how much memory you have, and you can see this SM. So if you remember, since this is Python, we're going to use Python. So if you remember, I said a full GPU has 108 streaming multiprocessors, or SMs. When you enable MIG, you lose 10. So we have 98. And now, since this is partitioned into 7 MIG instances, you get 14 SMs per instance. And this is exactly what you see here. So this is a MIG instance, 1G, 5GB, time sliced. So we can have more processes running on this single instance. And that's it. I think this is all I wanted to show as part of this demo. If there are any questions.
Thank you, Jana.
Thank you. Yes, Thomas.
Nothing,
No,
he's
I was
chatting.
just thank you. Thank you.
Hello.
No question. It was very clear. It's very interesting to see how it works, because I play a bit with a physical server but not on Kubernetes yet. So very good presentation. Thanks.
Thank you very much for attending. Right, so I
Okay.
think if we don't have
Mhm.
questions, we can stop the recording. I'll stop
Sure.
sharing.
You want to stop recording?